realize We'll start in about 5 minutes at 8 o'clock. Well, it's finally 8 o'clock. Let's go ahead and get started. We're going to work on section 8.2, and if there's any time left, we'll review section 8.1, and we'll review other things too if there's time. Okay, but we'll start 8.2. I'll try to make sure that everything is on camera. Section 8.2, simplifying radical expressions. In section 8.1, we assumed that a variable represented a real number so that, for example, the square root of x to the second equals the absolute value of x. In section 8.2 and beyond, we will assume that a variable represents a positive real number so that the absolute value symbols won't be necessary when computing things like the square root of x to the second. We can just write the square root of x to the second equals x. It's still correct to put the absolute value symbols around x, but if we're assuming that x is already a positive real number, the absolute value symbols are not necessary. Okay, the next thing that we'll discuss is the product property of radicals. So if we let n be a positive integer, and then if the nth root of a and the nth root of b are real numbers, then the nth root of the product of a and b, that is the nth root of a times b, is equal to the nth root of a times the nth root of b. We will be applying this product property of radicals when simplifying radicals of different indexes, square roots, cubed roots, and so on. Okay, so the product property of radicals will be applied to simplify radicals with more complex radicands than were encountered in section 8.1. And I'll explain a procedure for simplifying a radical with index 2. Remember from section 8.1, a square root is a radical with index 2. So in step 1, we identify the largest perfect square factor of the radicand. And then in step 2, we write the original square root as a product of two square roots, where the radicand of one of those two square roots is the largest perfect square factor found in step 1, and the radicand of the other square root is the radicand of the original square root divided by the largest perfect square factor. When you see a few examples, this procedure will make more sense if it doesn't already. In step 3, we simplify the square root of the perfect square, and we will multiply that by the other square root. Okay, so this procedural description will be demonstrated in several examples. Okay, first we will simplify the square root of 20. So, yeah, there's a comment about leaving more time for notes. One thing you can do is you can pause the YouTube live and then start again. And even though you won't be, when you start up again, you won't be at the same place. You can still watch the entire video until it's complete. That's an option. Okay, so the square root of 20, we note that 20 is not a perfect square. The largest factor of 20 that is a perfect square is 4, and 4 times 5 is 20. So we can rewrite this as the square root of 4 times 5. And the reason I'm writing it as the square root of 4 times 5 is because 4 is the largest factor of 20 that's a perfect square. Now we apply the product property of square roots. the square root of 4 times 5 can be written as the square root of 4 times the square root of 5. And then we simplify the square root of 4, which is 2, and our final result is 2 times the square root of 5. Okay, in the next example, simplify the square root of 63. 63 is not a perfect square. The largest factor of 63 that is a perfect square is 9. 9 times 7 is 63. So we will rewrite the square root of 63 as the square root of 9 times 7. And then apply the product property of square roots. The square root of 9 times 7 is the square root of 9 times the square root of 7. And then we simplify the square root of 9 to that simplifies to 3. So the simplified result is 3 times the square root of 7. And the next example, simplify the square root of 75. 75 is not a perfect square. The largest factor of 75 that is a perfect square is 25. 25 times 3 is 75. So we rewrite this as the square root of 25 times 3. And then we can write this as the square root of 25 times the square root of 3. And finally, the square root of 25 is 5. So our simplified answer is 5 times the square root of 3. Yeah, another comment about the video being watched after the fact. Yes, the recordings of the YouTube Live class sessions will be on YouTube to view at any time after the live session. Okay, the next one, the square root of 98. 98 is not a perfect square. The largest factor of 98 that is a perfect square is 49. 49 times 2 is 98. So we will rewrite the square root of 98 as the square root of 49 times 2. And then write it as the square root of 49 times the square root of 2. And the square root of 49 is 7. And so our simplified answer is 7 times the square root of 2. Okay, now we'll do some square roots involving variables. The first one, the square root of x to the 15th. If you remember from section 8.1, if you have a variable with an exponent, anytime that the exponent is a multiple of 2 or an even integer, then it's considered a perfect square. The exponent 15 is not a multiple of 2. It's an odd number. But the largest factor of x to the 15th that is a perfect square is x to the 14th. And x to the 14 times x is x to the 15th. So we're going to rewrite this as the square root of x to the 14th times x. Remember, x by itself means x to the first. So on the inside of the square root, we're just applying one of the properties of radicals. Okay, so the next step, we write the square root of x to the 14th times the square root of x. And the square root of x to the 14th, remember the index of a square root is 2. So to simplify the square root of x to the 14th, we write x to the 7th because 14 divided by 2 is 7. And then we multiply x to the 7th times the square root of x. In the next example, it's a similar type of situation. the exponent is odd. The largest factor of y to the 7th that is a perfect square is y to the 6th. Y to the 6th times y is y to the 7th. So we can rewrite this as the square root of y to the 6th times y. And then apply the product property of radicals. This can be written as the square root of y to the 6th times the square root of y. And then we can simplify the square root of y to the 6th. The square root of y to the 6th is y to the 3rd, because 6 divided by the index 2 is 3. And so our final answer is y to the 3rd times the square root of y. Okay, next we'll do a couple of examples that involve numerical factors as well as variable factors. The square root of 18x to the 27th. Well, we do this in pieces. The largest perfect square of 18 is 9. 9 times 2 is 18. And the largest perfect square factor of x to the 27th is x to the 26th. Okay, so we can rewrite this as the square root of 9x to the 26th times 2 times x. You can see what I'm doing. I'm putting the perfect square factors farther to the left. And you can verify that you've done it correctly just by multiplying. Then we can apply the product property of radicals and write this as the square root of 9x to the 26th times the square root of 2x. And then the square root of 9 is 3. The square root of x to the 26th is x to the 13th. And then we multiply that by the square root of 2x. Okay, so this is the simplified result. Okay, the next one, the square root of 72y to the 41st. The largest factor of 72 that's a perfect square is 36. 36 times 2 is 72. The largest factor of y to the 41st that is a perfect square is y to the 40th. So we'll rewrite this, putting the perfect square factors farther to the left. So 36 is a perfect square factor of 72. Y to the 40th is a perfect square factor of y to the 41st. And then we multiply that by the remaining factors, which in this case are just 2 times y. And then we can write this as the square root of 36y to the 40th times the square root of 2y. And the square root of 36 is 6, so 6 is outside of the square root. The square root of y to the 40th is y to the 20th. And so our final answer is 6y to the 20th times the square root of 2y. Square root of 2y. Okay, if you need to pause to write everything down, go ahead and pause the video and then hit play when you're ready to resume. Okay, the next part, we'll discuss a procedure for simplifying a radical with index 3, or a cube root. The procedure is very much like the previous one. It's just that now we're simplifying cube roots. Okay, so if you have a cube root, that means index 3, identify the largest perfect cube factor of the radicand. And then in step 2, write the original cube root as a product of two cube roots, where the radicand of one of those two cube roots is the largest perfect cube factor found in step 1, and the radicand of the other cube root is the radicand of the original cube root divided by the largest perfect cube factor. In step 3, simplify the cube root of the perfect cube and multiply it by the other cube root. So this procedural description above will be demonstrated in several examples. Okay, if you need to pause to write those notes down, you can. And we'll proceed with some examples. Yeah, this first one, simplify the cube root of 40. The largest factor of 40 that's a perfect cube is 8. 8 times 5 is 40. So we can think of this as the cubed root of 8 times 5. And then we can write it as a product of cube roots, the cube root of 8 times the cube root of 5. And then the cube root of 8 is 2. And we multiply 2 times the cube root of 5. Okay, so if you know what the perfect cubes are, that helps greatly. The next one, the cube root of negative 54. One thing that's different about a cubed root compared to a square root is that a cubed root of a negative real number is a negative real number, whereas a square root of a negative real number is not even a real number. So we can simplify this, the cubed root of negative 54. 27 is a factor of 54, and 27 is a perfect cube because 3 to the third power is 27. But since the radicand is negative 54, I want to write this as the cubed root of negative 27 times 2. And then we'll write it as a product of cubed roots, the cubed root of negative 27 times the cubed root of 2. And then the cubed root of negative 27 is negative 3. So this simplifies to negative 3 times the cubed root of 2. In the next example, simplify the cubed root of negative 250. Okay, well, the largest perfect cube factor of negative 250 is negative 125. Right, I should say the largest one is positive 125 because 5 to the third power is 125. And negative 125 times 2 is negative 250. So I want to think of this one as the cubed root of negative 125 times 2. And then write this as a product of cubed roots. The cubed root of negative 125 times the cubed root of 2. And the cube root of negative 125 is negative 5, because if you raise the number negative 5 to the third power, you get negative 125. So this simplifies to negative 5 times the cube root of 2. Okay, the next one, simplify the cube root of 128. Well, 8 is a perfect cube factor of 128, but it's not the largest of the perfect cube factors. 64 is a perfect cube because 4 to the third power is 64, and 64 times 128, sorry, 64 times 2 is 128. So we can write this as the cubed root of 64 times 2. Even if you only used the cubed root, or the perfect cube 8 in the factorization, you could still make it work. It would just be a little bit longer process. Okay, but since 64 is a perfect cube and it's a factor of 128, we write the cubed root of 64 times 2. And so that's the cubed root of 64 times the cubed root of 2. And the cubed root of 64 is 4. So we get 4 times the cubed root of 2. Here's some variable examples. Remember from section 8.1 that if you have an exponent that is a multiple of 3, it is considered a perfect cube. The exponent 10 is not a multiple of 3, but the largest factor of x to the 10th that does have an exponent that's a multiple of 3 is x to the 9th. And x to the 9th times x is x to the 10th. Okay, so we will write this as the cubed root of x to the 9th times x. And then we'll write it as a product of cubed roots. The cubed root of x to the 9th times the cubed root of x. And then the cubed root of x to the 9th is x to the 3rd, because the exponent 9 divided by the index 3 is 3. And so our final answer is x to the 3rd times the cubed root of x. That is our simplified result. Okay, the same sort of reasoning for the next example, the cubed root of y to the 26th. The exponent 26 is not a multiple of 3. The largest factor of y to the 26th that is a perfect cube, or that has an exponent that is a multiple of 3, is y to the 24th. And y to the 24th times y to the 2nd is equal to y to the 26th. So we will rewrite this as the cubed root of y to the 24th times y to the 2nd. And then we'll write it as a product of cubed roots, the cubed root of y to the 24th times the cubed root of y to the 2nd. And then since y to the 24th is a perfect cube, we can simplify the cubed root of y to the 24th. That simplifies to y to the 8th, because 24 divided by 3 is 8. And so our final answer is y to the 8th times the cubed root of y to the 2nd. Okay, the next two examples involve radicands that have a numerical factor as well as a variable factor. So we just combine the sorts of things that we did in the previous examples. The largest factor of 81 that is a perfect cube is 27. 27 times 3 is 81. And the largest factor of x to the 19th that is a perfect cube is x to the 18th, because 18 is a multiple of 3. So we'll rewrite this as the cubed root of 27x to the 18th times 3x. And then we'll write it as the cubed root of 27x to the 18th times the cubed root of 3x. And then we can simplify the cubed root of the perfect cube factors. The cubed root of 27 is 3. The cubed root of x to the 18th is x to the 6th, because 18 divided by 3 is 6. And so our final answer is 3 times x to the 6th times the cubed root of 3x. Okay, in the next example, the cubed root of negative 24y to the 41st. Remember that negative 8 times 3 is negative 24, and negative 8 is a perfect cube because the number negative 2 to the third power is negative 8. The largest factor of y to the 41st, that's a perfect cube, is y to the 39th. 39 is a multiple of 3. Okay, so we'll rewrite this as the cubed root of negative 8 times y to the 39th times 3 times y to the 2nd. And then the cubed root of negative 8 y to the 39th times the cubed root of 3y to the 2nd. And then finally, we'll simplify the cubed root of the perfect cubes. The cubed root of negative 8 is negative 2. And the cubed root of y to the 39th is y to the 13th, because 39 divided by the index is 13. And then we have to multiply negative 2 times y to the 13th times the cubed root of 3y to the 2nd. Okay, this sort of procedure can be extended to radicals with higher order indexes. We'll do just a couple of examples. The fifth root of n to the 32nd. Well, a perfect fifth power is a term whose exponent is a multiple of 5. The exponent 32 is not a multiple of 5, but 30 is a multiple of 5. So n to the 30th is the largest factor of n to the 32nd that is a perfect fifth power. Okay, so we'll rewrite this as the fifth root of n to the 30th times n to the 2nd. And the fifth root of n to the 30th simplifies to n to the 6th, because 30 divided by 5 is 6. And then we multiply n to the 6th times the fifth root of n to the 2nd. Okay, we'll do one with a fourth root. On this one, the fourth root of 32 times m to the 20th. The largest factor of 32 that is a perfect fourth power is 16, because 2 to the fourth is 16. 16 times 2 is 32. M to the 20th is a perfect fourth power because the exponent 20 is a multiple of 4. Okay, so we'll rewrite this as the fourth root of 16 times m to the 20th times 2. And then that's the fourth root of 16 times m to the 20th times the fourth root of 2. And then we can simplify the fourth root of the perfect fourth powers. The fourth root of 16 is 2. The fourth root of m to the 20th is m to the 5th. The exponent is 5. 20 divided by 4 is 5. And then the final answer, 2 times m to the 5th times the fourth root of 2. Okay, if you need to pause the live stream, go ahead and pause, and I'll go ahead and start with the next part of section 8.2. Okay, the second part of section 8.2 involves quotients of radicals. So first we talk about the quotient property of radicals. Let n be a positive integer. If the nth root of a and the nth root of b are real numbers and b is not equal to 0, then the nth root of a divided by b is equal to the nth root of a divided by the nth root of b. Okay, so we will apply this quotient property of radicals in several examples. Okay, in this first one, we have a radical with a quotient, and the index of the radical is 2. Remember that when the index is 2, it's just the square root. So it's not required to write the index 2 for a square root, but you can if you want to. Okay, so one way to go about this, first check to see if the quotient can be written in lower terms. This one cannot be written in lower terms. So we can write it as a quotient of square roots using the quotient property of radicals. So I'll do that. I'll write in the numerator the square root. I'm not going to bother with the index 2 because it's the same thing. The square root of 50m to the 7th in the numerator, and in the denominator, the square root of 49 times n to the 14th. And then we focus on simplifying the radical, the square root in the numerator and the square root in the denominator. Well, we can simplify the denominator completely, because in the denominator we have the square root of perfect squares. 49 is a perfect square, and so is n to the 14th. So we can just simplify the square root of 49 and write 7, and the square root of n to the 14th is n to the 7th, because 14 divided by the index 2 is 7. And then in the numerator, we have a little bit more to do. The largest factor of 50 that's a perfect square is 25. 25 times 2 is 50. And the largest factor of m to the 7th, that's a perfect square, is m to the 6th. M to the 6th times m is m to the 7th. Okay, so we'll rewrite the numerator as the square root of 25m to the 6th times 2m. Okay, then we can write it as the square root of 25m to the 6th times the square root of 2m divided by 7n to the 7th. And finally, in the numerator, the square root of 25 is 5. The square root of m to the 6th is m to the 3rd. And so in the numerator, we have to multiply 5m to the 3rd times the square root of 2m. And the denominator is 7n to the 7th. Okay, and the next example up here on the right, the square root of 300x to the 6th over 169y to the 8th. Well, the quotient cannot be written in lower terms, so let's go ahead and write it as a quotient of square roots. So in the numerator, we have the square root of 300x to the 6th. And in the denominator, we have the square root of 169y to the 8th. And in the denominator, note that 169 is a perfect square. The square root of 169 is 13. And the square root of y to the 8th is y to the 4th. So we'll rewrite the denominator in simplified form. The square root of 169 is 13. The square root of y to the 8th is y to the 4th. And then in the numerator, the largest factor of 300 that's a perfect square is 100. 100 times 3 is 300. And x to the 6th is a perfect square because the exponent 6 is a multiple of 2. Okay, so we'll rewrite the numerator as the square root of 100x to the 6th times 3. And that's the square root of 100x to the 6th times the square root of 3. And divided by the denominator, 13y to the 4th. And finally, the square root of 100 is 10. The square root of x to the 6th is x to the 3rd. And so in the numerator, we have 10 times x to the 3rd times the square root of 3 divided by 13y to the 4th in the denominator. Okay, a couple more examples on this page. Okay, the cubed root of 375 divided by 27. The largest factor of 375, that's a perfect cube, is 125. 125 times 3 is 375. And the denominator, 27, is a perfect cube. So even though we could reduce the fraction to lower terms, since the denominator is going to simplify, so I'll show you what I mean. If we simplified the fraction, we could still make it work, but we would be making more work for us in the long run. So since the denominator simplifies to 3, the cube root of 27 is 3, then we just focus on simplifying the numerator. The largest factor of 375, that's a perfect cube, is 125. So we'll rewrite the numerator as the cube root of 125 times the cube root of 3. And then the final result, the cube root of 125 is 5, so 5 times the cube root of 3, all divided by 3. Well, at some point in the near future, you'll, if you're wondering why I didn't reduce that fraction to lowest terms, it will become more apparent before the week is over. I'll just mention, in general, when simplifying quotients of square roots or quotients of radicals, we never want a radical to be left in the denominator. Okay, but more about that on a later day. Okay, in the next example, the cube root of negative 24 over 125. We'll write this as the cube root of negative 24 over the cube root of 125. And we can simplify the denominator. The cube root of 125 is 5. 125 is a perfect cube. So we'll go ahead and do that in the denominator. And then we can simplify the cube root of negative 24. So negative 8 is a perfect cube. Negative 8 times 3 is negative 24. So we'll rewrite the numerator as the cube root of negative 8 times 3. And then this is the cube root of negative 8 times the cube root of 3. And the denominator is 5. And then the last step, the cube root of negative 8 is negative 2. So in the numerator, we have negative 2 times the cube root of 3. And divided by 5. Okay, so that's the simplified result of that one. Okay, we have a few minutes left, so I will go ahead and review section 8.1. We already covered that before, but it's been a couple of weeks maybe since you've seen that. Okay, so this is the section 8.1. Well, as you know, this symbol is called the radical sign. And the number or algebraic expression that's inside the radical is called the radicand. So for example, in this square root of 7, the radicand is 7. That's the number inside. For this example, the radicand of the square root of x is just x. That's the variable part on the inside. In general, if n is a positive integer, then the symbol, you see the n there, is called the radical sign with index n. So you're probably pretty familiar with that by now. The index of a radical, or when the index of a radical is n equals 2, the radical sign is called the square root. So for square roots, you can include the index 2 if you want, but if you don't, it's still understood to be the square root. Okay, let's move down to this line. Let a be a number. Then this symbol is the principal square root of a, which means that it's positive. It's not negative. And so the principal square root of a is equal to the number whose square is a. Okay, so you're familiar with that by now. If the square root of a equals m, then a is equal to m to the second. Okay, so if you know a bunch of the perfect square whole numbers, that can help you when simplifying square roots. For example, we know down here, we know that 49 is a perfect square, and the square root of 49 simplifies to 7, because since 7 to the second equals 49 is a perfect square. And here's a short list of perfect square whole numbers. And you can generate a list of perfect squares simply by squaring the whole numbers. So for example, 289 is just 17 squared. And you've seen a bunch of examples today where we simplified square roots of perfect squares. And then remember, the square root of a negative real number is not a real number. Okay, the next part, well, we're down to less than 3 minutes. So we saw some of this already today. So if x is a real number, remember, if x can be positive, negative, or 0, then the square root of x squared has to be written as the absolute value of x. And a real number, capital X, can be positive, negative, or 0. So this is just an explanation why the absolute value of symbols must be surrounding x when appropriate. And we also reviewed today earlier that exponents with variable terms with exponents that are multiples of 2 are perfect squares. So square roots of variable parts with even integers simplify pretty nicely. Okay, we're down to less than a minute. So keep in mind, I have other videos on YouTube that you can watch. I've already posted the videos that have gone completely through all of the Chapter 8 material, including Chapter 7, which is the Test 3 material. So use those videos as much as necessary, and I guess we'll close for today. But we'll be back here again tomorrow at the same time. It's about 2 minutes till we'll start right at 9 o'clock. Okay, it's 9 o'clock. We'll go ahead and start section 8.2. So notice in the comments that if you're trying to take notes and I'm going too fast, you can pause and write down the notes. But I will go at not quite as fast as a reading pace, but fairly quickly. So section 8.2 is simplifying radical expressions. You might remember in section 8.1, we assumed that a variable represented a real number, so that, for example, the square root of x squared is equal to the absolute value of x. Since this is a principal square root, its value has to be positive. And so if x is a negative real number, x squared is positive, and so the positive square root of a positive real number must be positive. But in section 8.2 and beyond, we will assume that a variable represents a positive real number so that the square root of x squared is just equal to x. It won't be necessary to use the absolute value symbols if we're already assuming that x is positive. If you use the absolute value symbols, it's still correct. It's just not necessary. Okay, we'll today talk for a while about the product property of radicals. So let n be a positive integer. If the nth root of a and the nth root of b are real numbers, then the nth root of a times b equals the nth root of a times the nth root of b. The product property of radicals will be applied to simplify radicals with more complex radicands than we encountered in section 8.1. So here's a procedure that you can follow, and we'll do a bunch of examples where we apply this procedure in a few minutes. So first we'll start with the square root. The procedure for simplifying a radical with index 2, that's the square root. We identify the largest perfect square factor of the radicand, and then we write the original square root as a product of two square roots, where the radicand of one of those two square roots is the largest perfect square factor that was found in step 1, and the radicand of the other square root is the radicand of the original square root divided by the largest perfect square factor. In step 3, we simplify the square root of the perfect square and multiply it by the other square root. The explanation of this procedure might sound more complicated than it really is, and so we'll do several examples and you'll see how it works. Okay, if you need to pause the live stream so that you can write the notes, then do so right now, but we'll go ahead and continue. Okay, the first one, simplify the square root of 20. 20 is not a perfect square, but the largest factor of 20 that is a perfect square is 4. 4 times 5 is 20. So we'll rewrite the square root of 20 as the square root of 4 times 5. And then we'll apply the product property of square roots. The square root of 4 times 5 is the square root of 4 times the square root of 5. And we can simplify the square root of 4 to 2, so our final answer is 2 times the square root of 5. In the next example, simplify the square root of 63. 63 is not a perfect square. The largest factor of 63 that is a perfect square is 9. 9 times 7 is 63. So we can rewrite this as the square root of 9 times 7. Then we'll apply the product property of square roots. The square root of 9 times 7 is just the square root of 9 times the square root of 7. And then the square root of 9 simplifies to 3, and so our final result is 3 times the square root of 7. Here we'll do a few more examples involving radicands that are whole numbers. The square root of 75. 75 is not a perfect square. The largest factor of 75 that is a perfect square is 25. 25 times 3 is 75. So we'll rewrite the square root of 75 as the square root of 25 times 3. And the square root of 25 times 3, using the product property radicals, is the square root of 25 times the square root of 3. And then the square root of 25 is 5, so our simplified result is 5 times the square root of 3. The next example, the square root of 98. The largest factor of 98 that's a perfect square is 49. 49 times 2 is 98. So we'll rewrite the square root of 98 as the square root of 49 times 2. And then this can be written as the square root of 49 times the square root of 2. And then we simplify the square root of 49 to 7, so our final result is 7 times the square root of 2. Okay, with variables and exponents, we apply the same procedure. Remember that variables with exponents are perfect squares if the exponent is a multiple of 2, or if it's an even number. The exponent 15 is not even, so x to the 15th is not a perfect square. The largest factor of x to the 15th that is a perfect square is x to the 14th. And x to the 14th times x is x to the 15th. So we're going to rewrite the square root of x to the 15th as the square root of x to the 14th times x. Remember that x by itself means that the exponent is 1. We just don't normally write the exponent 1. Okay, then in the next step, we'll write this as the square root of x to the 14th times the square root of x. And then we can simplify the square root of x to the 14th. That simplifies to x to the 7th. What we did, or what you can do, since the index of a square root is 2, we don't normally write the 2. Divide 14 by 2 to get x to the 7th. And so the simplified result of this one is x to the 7th times the square root of x. In the next example, simplify the square root of y to the 7th. The exponent 7 is not an even number. The largest factor of y to the 7th that's a perfect square is y to the 6th. So we'll rewrite it as the square root of y to the 6th times y. And then we can rewrite the square root of y to the 6th times y as the square root of y to the 6th times the square root of y. And the square root of y to the 6th simplifies to y to the 3rd, because the exponent 6 divided by the index 2 is 3, and then we multiply y to the 3rd times the square root of y. In the next pair of examples, we have radicands that involve numerical factors as well as variable factors. So we want to simplify the square root of 18x to the 27th. We're just going to combine what we did in the previous examples. So first, we focus on the numerical coefficient 18. The largest factor of 18 that's a perfect square is 9. And the largest factor of x to the 27th that's a perfect square is x to the 26th. So we'll rewrite this as the square root of 9x to the 26th times 2x. So I'm just putting the perfect square factors farther to the left, and the remaining factors farther to the right. And then we'll rewrite this as the square root of the perfect square factors, the square root of x, square root of 9 times x to the 26th multiplied by the square root of 2x. And then finally, we can simplify the square root of 9x to the 26th. The square root of 9 is 3, and the square root of x to the 26th is x to the 13th, because 26 divided by 2 is 13. So our final answer is 3 times x to the 13th times the square root of 2x. That's the simplified result. The next example is similar to what we just did. Simplify the square root of 72y to the 41st. The largest factor of 72, that's a perfect square, is 36. 36 times 2 is 72. And the largest factor of y to the 41st, that's a perfect square, is y to the 40th. So we'll rewrite this as the square root of 36 y to the 40th times 2y. You can always verify that you're doing it correctly by multiplying the terms. And I have the perfect square factors on the left. So we'll write this as the square root of 36y to the 40th multiplied by the square root of 2y. And then we can simplify the square root of the perfect square factors. The square root of 36 is 6. The square root of y to the 40th is y to the 20th, because 40 divided by the index 2 is 20. And so our final answer is 6y to the 20th times the square root of 2y. Okay, if you need a little bit extra time writing down what I've written, go ahead and pause, and I'll start the next part. In this next part, we follow a procedure for simplifying a radical with index 3, or a cube root. The procedure will sound very much like the other procedure that we just discussed about simplifying square roots. So in step 1, we identify the largest perfect cube factor of the radicand. And then we write the original cube root as a product of 2 cube roots, where the radicand of one of those 2 cube roots is the largest perfect cube factor found in step 1, and the radicand of the other cube root is the radicand of the original cube root divided by the largest perfect cube factor. Then in step 3, we simplify the cube root of the perfect cube and multiply it by the other cube root. And we'll do a few examples involving simplifying cube roots. If you would like more time to write down this procedure, go ahead and pause, and I'll start with the examples. Okay, the first example up here on the upper left, simplify the cubed root of 40. The largest factor of 40 that's a perfect cube is 8. 8 times 5 is 40. 8 is a perfect cube because 2 to the third power equals 8. So we'll rewrite the cube root of 40 as the cubed root of 8 times 5. And then the cubed root of 8 times 5 can be written as the cubed root of 8 times the cubed root of 5. And then the cube root of 8 simplifies to 2. So our final simplified answer is 2 times the cubed root of 5. Okay, the next one, the cubed root of negative 54. Remember that cubed roots of negative real numbers are negative real numbers. So there's a fundamental difference between radicals with indexes that are odd integers, such as 3, and compared to radicals with indexes that are even numbers, like the square root. The cubed root of a negative real number is a negative real number, whereas the square root of a negative real number is a number, it's just not a real number. So the cubed root of negative 54 is just a negative real number. Notice that a factor of negative 54 that's a perfect cube is 27. 27 times negative 2 is negative 54. But when we simplify this one to properly simplify it, we're going to write it as the cubed root of negative 27 times 2. And then we'll rewrite this as the cubed root of negative 27 times the cubed root of 2. And then the cubed root of negative 27 is just negative 3, because if you raise the number negative 3 to the third power, you get negative 27. So this simplifies to negative 3 times the cubed root of 2. Okay, the next example on the left, the cubed root of negative 250. 125 is a factor of negative 250, and 125 is a perfect cube. So we're going to rewrite the cubed root of negative 250 as the cubed root of negative 125 times 2. And then this is the cubed root of negative 125 times the cubed root of 2. And the cubed root of negative 125 is just negative 5. And so our final answer is negative 5 times the cubed root of 2. Okay, the next one, the cubed root of 128. Well, you might notice that 8 is a factor of 128, and 8 is a perfect cube. But there is a larger factor of 128 that's a perfect cube, larger than 8. That other factor is 64. 64 is a perfect cube because 4 to the third power is 64. So the more efficient way is to rewrite this as the cubed root of 64 times 2. And then this is the cubed root of 64 times the cubed root of 2. And the cubed root of 64 simplifies to 4. So this is 4 times the cubed root of 2. Okay, terms with exponents. can also be simplified. The cube root of x to the 10th. Remember that variables with exponents are considered perfect cubes if the exponents are multiples of 3. 10 is not a multiple of 3, so x to the 10th is not a perfect cube. The largest factor of x to the 10th that is a perfect cube is x to the 9th, because 9 is a multiple of 3. And x to the 9th times x is x to the 10th. So we can write this as the cubed root of x to the 9th times x. And then in the next step, we can write it as the cubed root of x to the 9th times the cubed root of x. And the cubed root of x to the 9th simplifies to x to the 3rd because the exponent 9 divided by the index 3, 9 divided by 3 is 3. So the final result is x to the 3rd times the cubed root of x. Okay, similar type of reasoning for this one. The cubed root of y to the 26th. 26 is not a multiple of 3, so y to the 26th is not a perfect cube. The largest factor of y to the 26th that is a perfect cube is y to the 24th. So rewrite this as the cubed root of y to the 24th times y to the 2nd. So if necessary, you might need to review section 5.2 on properties of exponents. Y to the 24th times y to the 2nd is y to the 24 plus 2, which is 26. Okay, in the next step, we write this as the cubed root of y to the 24th times the cubed root of y to the 2nd. And then we simplify the cubed root of y to the 24th. That simplifies to y to the 8th because the exponent 24 divided by the index 3 is 8. And so our final answer is y to the 8th times the cubed root of y to the 2nd. Okay, the next example, simplify the cubed root of 81x to the 19th. Well, the largest factor of 81 that's a perfect cube is 27. 27 times 3 is 81. The largest factor of x to the 19th that is a perfect cube is x to the 18th. 18 is a multiple of 3. So we will rewrite this as the cubed root of 27 x to the 18th times 3x. And then this is the cubed root of 27x to the 18th times the cubed root of 3x. And then on the left, we can simplify the cubed root of 27x to the 18th. The cubed root of 27 is 3. The cubed root of x to the 18th is x to the 6th, because 18 divided by 3 is 6. And so our final answer is 3x to the 6th multiplied by the cubed root of 3x. Okay, in our next example, simplify the cubed root of negative 24y to the 41st. Negative 8 is a factor of negative 24. Negative 8 times 3 is negative 24. The largest perfect cube factor of y to the 41st is y to the 39th. Y to the 39th times y to the 2nd is y to the 41st. So we'll rewrite this as the cubed root of negative 8y to the 39th times 3y to the 2nd, cubed root of that. And then we'll write this as the cubed root of negative 8y to the 39th times 3y to the second. Sorry, what I really want is multiplied by another cubed root of 3y, if you can read my sloppy writing. But in the next step, it should be clear. The cubed root of negative 8 is negative 2. The cubed root of y to the 39th is y to the 13th. And we multiply negative 2 times y to the 13th times the cubed root of 3y. Okay, a couple of more examples of simplifying radicals with higher indexes. This first one on the left, simplify the fifth root of n to the 32nd. A variable with an exponent is considered a perfect fifth power if the exponent is a multiple of 5. 32 is not a multiple of 5, but 30 is a multiple of 5. So the largest factor of n to the 32nd that is a perfect fifth power is n to the 30th. So we'll rewrite this as the fifth root of n to the 30th times n to the second, because n to the 30th times n to the second is n to the 30 plus 2, or n to the 32nd. And then this can be written as the fifth root of n to the 30th multiplied by the fifth root of n to the second. And the fifth root of n to the 30th is n to the 6th, because the exponent 30 divided by 5 is 6. And so our final answer is n to the 6th times the fifth root of n to the second. Okay, in the next example, simplify the fourth root of 32m to the 20th. The largest factor of 32 that's a perfect fourth power is 16. 16 is 2 to the fourth. And m to the 20th is a perfect fourth power because 20 is a multiple of 4. So we'll rewrite this as the fourth root of 16 m to the 20th times 2. And then we can rewrite this as the fourth root of 16m to the 20th times the fourth root of 2. And finally, the last step, the fourth root of 16 is 2. The fourth root of m to the 20th is m to the 5th, m to the power 5, because 20 divided by 4 is 5. So 2m to the 5th times the fourth root of 2 is the final result. Okay, if you need a little more time to write down what I have written, please pause and I'll start the next part. Okay, also in this section 8.2 is the quotient property of radicals. So if we let n be a positive integer, if the nth root of a and the nth root of b are real numbers and b is not equal to 0, then the nth root of a divided by b can be written as the nth root of a divided by the nth root of b. Okay, so we'll do some examples where we simplify quotients of radicals. So in this first one, we have a radical of a quotient with index 2. If it's an index 2, it's understood to be a square root. When the index is 2, you don't need to write it. First, notice that inside the radical, the quotient cannot be written in lower terms. So we might as well just go ahead and apply this quotient property of radicals, I'll have a square root of 50m to the 7th in the numerator, and in the denominator I'll have the square root of 49n to the 14th. I'm not going to bother writing the index 2 since the square root is the same. Notice the denominator simplifies pretty nicely because the denominator is, the radicand is a perfect square. So let's go ahead and simplify the denominator. The square root of 49 is 7, and the square root of n to the 14th is n to the 7th. And we have a little more to do in the numerator. The largest factor of 50 that's a perfect square is 25. 25 times 2 is 50. And the largest factor of m to the 7th that is a perfect square is m to the 6th. So we'll rewrite this as the square root of 25 m to the 6th times 2m. And then in the numerator, we'll write it as the square root of 25m to the 6th times the square root of 2m, and divided by 7n to the 7th. And then finally, we will simplify the square root of 25m to the 6th. That is 5m to the 3rd. So in the numerator, we write 5m to the 3rd times the square root of 2m. And this is divided by 7n to the 7th. Okay, the next example, simplify the square root of 300x to the 6th divided by 169y to the 8th. The quotient cannot be written in lower terms. It's already in lowest terms. So we'll rewrite this as the square root of 300x to the 6th in the numerator. And in the denominator, the square root of 169y to the 8th. The denominator simplifies nicely, so we'll go ahead and do that. 169 is a perfect square. The square root of 169 is 13. And y to the 8th is a perfect square. The square root of y to the 8th is y to the 4th. And in the numerator, the largest factor of 300 that's a perfect square is 100, and x to the 6th is a perfect square. So we can rewrite the numerator as the square root of 100 x to the 6th times 3. Okay, then we'll write it as the square root of 100 x to the 6th times the square root of 3 divided by 13y to the 4th. And then the square root of 100x to the 6th simplifies to 10x to the 3rd. So we have in the numerator 10x to the 3rd times the square root of 3, all divided by 13y to the 4th. Okay, we'll do a couple of quotients of radicals with cube roots. Okay, so this one, the cube root of 375 over 27. Let's write it as the cubed root of 375 over the cubed root of 27. The denominator simplifies to a whole number because 27 is a perfect cube. So the denominator, the cubed root of 27 is 3. And in the numerator, the cubed root of 375, the largest factor of 375 that's a perfect cube is 125. 125 times 3 is 375. So the numerator will write that as the cubed root of 125 times 3. And then we get the cubed root of 125 times the cubed root of 3, all divided by 3. And then the final step, the cubed root of 125 is 5. So in the numerator, we have 5 times the cubed root of 3. And in the denominator, we have 3. With some practice, you won't need to write every single step. But until you're comfortable with that, I would advise showing more work. Okay, in the next example, simplify the cubed root of negative 24 over 125. So let's write it as the cubed root of negative 24 over the cubed root of 125. The denominator simplifies nicely. The cubed root of 125 is just 5. And then in the numerator, the cubed root of negative 24, negative 8 is a perfect cube factor of negative 24. So we'll rewrite the numerator as the cubed root of negative 8 times 3. Okay, then we'll write the numerator as the cubed root of negative 8 times the cubed root of 3, and then that's divided by 5. And finally, the cubed root of negative 8 is negative 2. So the numerator is negative 2 times the cubed root of 3, and this is all divided by 5. Okay, that concludes our coverage of 8.2, but we're also going to cover the first part of section 8.3. If you need to pause so that you can write down everything that I've written, then do so at this time, and I'll start the next section. Okay, section 8.3. Okay, in section 8.3, we learn about rational exponents. Okay, in this sentence it says radicals can be written in rational exponent form. A rational exponent is an exponent that is an ordinary fraction in lowest terms. All of the properties that we learned about exponents in section 5.2, those apply to rational exponents. So sometimes I will remind you of what some of those properties of exponents are. Okay, so here's a definition. If we let n be a positive integer, well, we know about the nth root of a, but the nth root of a can be written in a different form called the rational exponent form. The nth root of a is equal to a raised to the exponent 1 divided by n. Okay, so we will practice converting radicals to rational exponent form. The square root of x. Well, remember what the index of a square root is. The index is 2. So the square root of x written in rational exponent form is x to the 1/2 power. So the exponent is 1/2. The cubed root of 15. This time the index is 3. So the cubed root of 15 is in rational exponent form. It's 15 to the 1/3 power. That is, the exponent is 1/3. The denominator of the exponent is the same as the index of the radical. The fourth root of n, well, the index of the radical is 4, so this is equivalent to n to the 1/4 power. So this time the exponent is 1/4. And then the fifth root of 11, that's just 11 to the exponent 1/5, or 11 to the power 1/5. Okay, so just notice, just in case some of the terminology is vague, each of those exponents is an ordinary fraction in lowest terms. And remember that a rational number is a number that can be written as an ordinary fraction. So that's what is referred to when it says rational exponent form. The exponents are rational numbers. Okay, we'll do some other examples where we go in the opposite direction. That is, convert the following expressions that are in rational exponent form, convert those to radical form. Okay, it's not too hard. On this one, 17 to the 1/2, the denominator of the exponent is 2, so that means the index of the radical is 2, or square root, and the radicand is 17. 17 is what goes inside the radical whose index is 2. A to the 1/4, the denominator of the exponent is 4, so the radical has index 4, and the radicand is A. A is what is inside the radical with index 4. So no doubt you see the pattern. 29 to the 1/6, the denominator of the exponent is 6, so the radical has index 6, and 29 is what goes inside that radical. Y to the 1/3, the denominator of the exponent is 3, so the radical has index 3, and y goes on the inside. Okay, so let's just, a couple of observations in those. If you see something with an exponent that's 1/2, it just means to take the square root of that number. And a more familiar radical is a cube root. So if you see something that has an exponent of 1/3, it just means to compute the cubed root of that number. Okay, so we'll try that with actual numbers. Let's simplify the following expressions with rational exponents. But don't bother converting them to radical form. Just evaluate those. 49 to the 1/2. That just means the square root of 49. And we know that the square root of 49 is 7. So 49 to the 1/2 simplifies to 7. 81 to the 1/4 is the fourth root of 81. 81 is a perfect fourth power because 3 to the 4th is 81. So the fourth root of 81 simplifies to 3. 32 to the 1/5, that just means compute the fifth root of 32. 32 is a perfect fifth power because 2 to the 5th power is 32. So the fifth root of 32 is just 2. And 64 to the 1/3, that's the cubed root of 64. And you'll remember that 64 is a perfect cube. 4 to the 3rd power is 64. So the cubed root of 64 is just 4. It's okay if you convert them to radical form first. It's just not necessary. So if you want, you could convert 49 to the 1/2 to the square root of 49. the principal square root of 49, and that's 7, and so on. Okay, we have about 5 minutes left. I'll just point out a couple of things here. You've noticed that some numbers are not only perfect squares, but they are perfect other powers. For example, 81 is a perfect square, and it's also a perfect fourth power. 64 is a perfect square and a perfect third power. So just being aware of those little details can be helpful. Okay, we'll go ahead and start the next part. This next part we'll finish tomorrow, but I'll at least show you what's coming. So we have this definition. This time let m and n be positive integers. And then the nth root of a to the m, so note that inside the radical is a raised to the exponent m. Applying the definition that we saw a little earlier, we can convert this to rational exponent form if we just raise a to the m to the 1 over n. And then if we apply a property from section 5.2, we can multiply those two exponents. 1 over n times m is m over n. So we can think of the nth root of a to the m as a to the m over n. And we can also rewrite this so that we have a to the 1 over n in parentheses, and the outer exponent is m. And you can verify that this is true if you multiply the exponent m times 1 over n, it's just m over n. But this means inside the parentheses, we just have the nth root of a, and the outer exponent is n. Okay, so all we were doing is applying definitions and properties of exponents to get those 5 equivalent expressions. So let's start converting these radicals. We'll stop with this example here in a couple of minutes. Convert the following radicals to rational exponent form. Okay, so here's a radical with index 7, and the radicand is x to the 4th. So I'll put what's inside the radical in parentheses, x to the 4th, and write the exponent 1/7. And then we can apply one of the properties of exponents by multiplying 1/7 times 4, and we can write it as x to the 4/7, because 1/7 times 4 is 4/7. Okay, this next one, inside the 4th, the radical whose index is 4 is 2y. So on this one, we'll write in parentheses 2y, and then the exponent is 1/4. So on this one, think of, on the inside of the parentheses, think of 2 as 2 to the 1st, and think of y as y to the 1st. And then applying one of the properties of exponents that we already learned, we can multiply the exponent 1/4 times each of those. And we can write this as 2 to the 1/4 times y to the 1/4. Okay, we'll stop there. There's a few seconds before 10 till, but tomorrow we will pick up from where we left off. And we will also go on to the next section, 8.4, after we complete section 8.3. So I'll see you tomorrow.